Okay, good morning. I guess the usual saying is I'm the last person between you and lunch. I suppose here the proper way of saying this would be this is the last person between now and you gambling all the rest of the money so you can walk home. It's a long walk for most of us. So thank you for being here this morning. My name is Alex Blyne. I'm the director of the Institute of Transportation Studies at UC Berkeley and the faculty in electrical engineering and computer science. Today I'm going to talk about solving traffic problems using autonomous vehicles, and that's work which has been done at UC Berkeley over the last couple of years with some of the people who are here in the audience, Kathy Zhang, who here is in the front, and Feng Yu, who is somewhere. So if you think about the future of mobility, where mobility is viewed broadly, there's a lot of different visions of what that future might look like. There are insane places like Neom in the north of the Kingdom of Saudi Arabia, which are building a city from scratch with a complete new infrastructure, kind of like what Dubai did a few years ago, but from scratch. There's places like the Jurong district in Singapore, in which the instrumentation of the infrastructure has been pushed to its extreme. And of course, there's a lot of visionary approaches, like CarTube for LA, where you might have high-speed underground traffic for specific types of vehicles through the Boring Company, which is a company that is doing that. Hyperloop, which has interesting viability from an economic standpoint. And the future of flying cars is already here, and that is going to happen no matter what. And so one of the questions that people ask when it comes to autonomy of traffic is, in a world of self-driving vehicles where it's 100% of the vehicles are self-driving or X% of the vehicles are self-driving, is the energy footprint of transportation going to be better or worse? And this graph, which used to be the graph that Ruben Sarkar, the Deputy Assistant Secretary of Energy in the previous administration, was showing, which is taken from an article from Don McKinsey and co-authors from UW, gives an interesting answer to that question. And if you read the paper, what you will find is that in the future of autonomy or some form of autonomy, the energy footprint of mobility could go up by 200% or go down by 60%. And this kind of tells you why. So you can imagine a future in which all the vehicles are on their freeway empty, stuck, because you're sending your self-driving vehicle pick up your child at school and it gets stuck on the freeway, or it drops you off at work and then keeps circling in the city because it's not finding parking. So that's how you get to the 200%. Or the minus 60% is a kind of a well-organized system in which traffic flow is smoothed by self-driving vehicles, in which high-speed platooning is in favor of energy efficiency, and so on and so forth. And so that graph, which is going to be a guideline for the Department of Energy for I think quite some time, is a motivation for the work we do and the work I'm going to present today. And I think the way it ties into this conference and this audience in general is that we've reached a point in which both cloud computing, modeling, and machine learning have been enabled to a level where the economies of scale make it that you can really simulate things at very large scale in a way that has never been done before to enable new approaches, in particular in mixed autonomy. And so, traditionally, the world of modeling in transportation, a very kind of an ancient field, if you will, has separated the different layers of modeling in different levels here. There are people who do simulations of a city like San Francisco or even the Bay Area and will model millions of agents moving throughout the day. Of course, you can't do it at the level of accuracy that would describe what the person is doing every second. Then there are people who do traffic engineering who try to model what vehicles are doing on a second-by-second basis, and you can do it at some scale. But if you really want to get to the dynamics of the vehicle or even what's happening, you can't do it at the scale of the city like Los Angeles. And so I think that this kind of a telescopic diagram here kind of shows or gives an idea of what the scales have been in the past in terms of how big can you go when you simulate a city. And so I think the good news of today's talk is that this level, which used to be a pretty small level, has gotten quite big, enabled by the AWS cloud, but also enabled by other things. So to give you a sense of the kind of a no big deal state of the art, This is a IMSUN simulation tool. It's doing some comparison of what happens when people don't have phones versus 20% have phones. And it shows a lot of the features of traffic. The point is not to talk about that case study. The point is to show that simulation on the I-210 corridor in Los Angeles, and just to give you a sense of the type of scale that are no big deal scales today in terms of simulation. So that simulation here probably has tens of thousands of vehicles going from all kinds of origins to all kinds of destinations. It has different types of vehicles. You can see trucks, you can see buses, you can see all kinds of stuff. There's routing options that are being changed as the simulation progresses, and so on and so forth. This is a type of simulation called micro-simulation. And that's something you can generate quite easily from software that is available online. For example, that is available commercially, sorry. So IMSUN and vSim are the two leaders in this field. And then Sumo is their counterpart, which is completely open source, which is not commercial. And the takeaway message here is that I think 5 years ago or 10 years ago, it would not have been possible to run a simulation at that scale. And it would have been crazy to think that you calibrate it. It's one thing to simulate something, it's something else to simulate it in a way that is close to reality. 5 years ago, you could not run it on the cloud. And 20 years ago, I mean, it was, if you had told someone you'd run something like this, people would have told you you're crazy. Today, it's not a big deal to do this kind of simulation. Calibrating is a bit harder, so usually there are companies that will sell you a calibration process for that for maybe $250,000 to $500,000, and if you're a city, that's what you buy because you want an accurate model, but it's not science fiction anymore. And so trying to summarize the underlying problems here, there's data problems, there's calibration problems, there's model computational problems, so essentially computational efficiency, and then of course there's machine learning problems. So data problems is an interesting problem because 10 years ago there probably was not enough data to calibrate the models, period, which is why at that time it was complete science fiction. Of course now with cell phone data and all the other types of digital traces we have, there is enough data to calibrate these models. The calibration is also something that, you know, with in the post Web 2.0 and crowdsourcing era, is something that there's been a lot of work in, particularly in machine learning. So that's something which is also in reach. What AWS and other clouds have enabled is the model computation, and that is for sure something that did not exist 2 or 3 years ago, because 2 or 3 years ago, none of the tools I've shown here were working on the cloud. And that has enabled deep reinforcement learning, which is a new thing in this field, which is, as I mentioned earlier, a bit antiquated today. And so, of course, we don't know, how fast this thing will develop. And of course, even though it's feasible to do this kind of work at the scales today, you still can't do it at the scale even of Las Vegas. That'd be too big if you want to try to simulate and optimize everything. So the topics I'm going to talk about today mostly have to do with demand and routing and how they are calibrated. They're going to also have a little bit to do with the computation cost and what you have to pay to make it work, and mostly about what has happened over the last literally 2 years, which is kind of the first happy marriage, if you will, between kind of a recent advances in machine learning and that world, which is a very traditional world, but which is all over the cities because that's their simulation tools. And so it's almost like a call of action here in that, the effort I'm going to summarize today are the first integration of cloud plus deep reinforcement learning plus microsim historically. However, it's just the beginning. And it's just the beginning in the sense that I'll show through some examples the successes that we've had and the successes that the community has had. But there still needs to be a lot of advances algorithmically, as well as computationally, for it to be tractable and for it to really reach its full potential. And so that's really what we'd like to do is over the next 2 years really bring it to the state where you could do these simulations and literally migrate some policy directly to an actual physical vehicle and to a set of vehicles in a meaningful manner. So let's just jump back in history for 2 minutes. This is the first time in history, in 1935, that someone actually measured a traffic jam. The person on that picture is Bruce Greenshield. He somehow used to live in Ohio, and there used to be an agricultural festival where people would gather, and there were probably a couple hundreds or maybe thousands of people that would gather to compare their products, their whatever they were selling. And that was enough to create traffic jams, which in Ohio probably had never happened ever before. He measured kind of a first empirical model that ended up being a phenomenal diagram. If you Google search a phenomenal diagram transportation, you'll find thousands of articles throughout history, almost half a century, who have used it. And it, 20 years later, gave rise to the first dynamic models of traffic, and this is back in the community of hydrodynamics, people modeling traffic like fluids using partial differential equations and other more advanced mathematical tools that are commonly used in applied math. Then, fast forward almost half a century, Sugiyama in Japan did that interesting experiment that as soon as it was posted on YouTube went viral. Now, viral at the time meant 2 million views. This is 10 years ago. Essentially in that experiment, he asked people to drive in circles at 25 miles an hour, or there was a target limit. And the only directions he gave to people is just follow the person in front of you and keep your distance and don't get in a crash. So it's a pretty boring video to watch. But it is actually pretty amusing that if you keep watching that video, what you will see is that people actually cluster and bundle, and that whole traffic becomes pretty unstable. Unstable in the sense that these guys are stopped now in the back, and these guys are going really fast to catch up, and then at some point, that bottleneck has moved backwards, and essentially there's a backwards moving traffic jam that keeps self-perpetuating. So it's pretty telling, right? You're asking humans to drive at 25 miles an hour, and they can't even do it. But that is the explanation of a lot of the traffic jams that all of you have encountered on the freeways. Like, how many times have you been stuck in your car and you have no idea why? That's one of the reasons. Now, fast forward another 10 years. One of our former students, Dan Work, as with other colleagues, redid the experiment in Arizona. And what they did is they actually inserted a self-driving vehicle in the middle. So right now you can see this arrow is black. That means it's a human driving the car. But at some point, the arrow will turn red, and that's when, so you can see this is happening again. It's pretty bad oscillation. And now it turned red, and somehow what you see is that after a tiny bit of time, that car is able to stabilize the ring. And it's smooth. And you can see there's no more oscillations here. So that's crazy, right? Because that means with essentially 5% of vehicles, I mean, there's hope that you could actually fix a lot of the problems of traffic. At some point, it's going to disengage, and you're going to see that's going to happen again. And they don't do it on purpose. I mean, it says, like, you should try it with your children or with your colleagues or with your students or with whoever. These are pretty easy to create instabilities. OK, there's a fascinating number with that experiment. This is 42% savings in energy. So by inserting one vehicle in that ring, you can save 42% in energy, and that's not modeled, that's actually measured from the OBD2 ports of each of the other vehicles. So of course, it doesn't mean that you can save 42% of energy on freeway traffic, but probably that will translate into 10% of energy in freeway traffic, which if you think about a California freeway carries about 2,000 vehicles per hour per lane. So if you take someone like lane 101 as like 10 lanes, 5 both directions, that's a ton of energy, that's a ton of gas, that's a ton of savings for the environment. So that's a motivation for why I'm here today, but there's an angle with the cloud and with reinforcement learning that I want to talk about, because right now, all that work that I've shown, the previous work was an experiment. This work is model-based. Model-based means essentially there's a controller that runs in the self-driving vehicle. That controller has a mathematical model of its own vehicle as well as the other vehicles, and then it optimizes using model predictive control or any kind of controller technique that you can use to smooth the traffic. So now, so that means someone actually modeled the whole thing to make the controller work for that whole thing. So that's of course, what I want to supersede with machine learning. And so here is another numerical experiment that was run by Kathy Wu, another of our former grad students, who is now a professor at MIT. And I'm going to show you the same experiment in simulation and tell you why I'm showing you a simulation now. So this is using the software we developed that I'm going to describe at the end of the talk. And here what you see in this video is essentially the same setting. So we have the ring. The red car is the self-driving car. The blue car is the only car it can sense, so you can only see the person in front of you. And the white cars are just models of humans driving the car. So right now, it's just not automated, and now it just crossed that line, so it's certainly become automated. And what you can see is that the controller manages to achieve the same thing as the experiment. And now the whole thing stabilizes again. So probably now you're wondering, well, if there was an experiment in 2017 that worked, why the hell would you do a simulation in 2018? Because they did it in 2017. And there's one major difference. This 2017 run, that was a model-based controller. Someone had a model of the car and a model of the other drivers, came up with that control algorithm, and optimized the flow and succeeded. This here has no model. This is a policy that was developed by learning how cars behave by using a, quote, black box simulator of the ring and learning without knowing anything about the dynamics of the other cars, just by essentially looking at a reward function and making that reward function better. So in a sense, what happened between the 2017 and the 2018 here is that this was relying on half a century of models and explicit approaches, analytical models of traffic. This essentially is just relying on an accurate simulator. And that's very disruptive, because that means you do not really need to understand what's happening or the dynamics of a vehicle to achieve as good a result as you would with a model-based approach. And for all of you who have worked in model-based fields, you know that at some point that disruption has either completely changed your field or there's a likelihood that it will do so in the very near future. And so same types of saving. Actually, the funny part here is that without the model, you beat the actual model-based approach, but that's not the point really. The point is that this is the beginning of a complete new era in this field and in many fields. Between the first traffic jam measurements I showed you in 1935 and that first experiment, there's like 10,000 articles to model it. Then just on that experiment, on the ring experiment, lots of people have tried to study that. They've even invented funny names for it. They called it Jamiton or phantom jams, or there's all kinds of esoterical names coming from all kinds of universities. And there's at least 1,000 articles more or less focused on fixing that stability. And in a sense, you could argue that the 2017 result, which is pretty disruptive and amazing, it relied a lot on these 1,000 articles. And then with one article, you can beat it by essentially discarding anything that has been done over half a century and just using a calibrated simulator. So that should, at that point, when we realized that, we figured that there's something clearly new and disruptive to be done in this field. And that's when we started heavily investing in building these simulators, making them scale, which is why you need the AWS cloud or any other cloud. And then, of course, using the state-of-the-art reinforcement learning libraries, because that's how you optimize. So you could argue, OK, great deal, right? You just taught a self-driving vehicle to drive in a ring. What's the big deal? So here's another example of some. So now I'm going to show you a bunch of Lego blocks to make it harder and harder and harder. And every time the color scheme is going to be the same, the self-driving vehicle is going to be in red. Whatever it can see is in blue. So for example, this guy can sense the car in front and the car behind. And you'll see in some cases you need to sense everybody. In some cases you don't need to sense everybody. So it depends on the scenario. And then any white vehicle is essentially a model of a human driving a vehicle. You have no idea what it's doing. You can only see its effect through the blue vehicles. So let's try a double ring first. And if you're in the front, you can see that red car here. And you can see what it's doing, right? It's essentially behaving like a jerk by making sure that none of the blue cars it's watching back can pass him, right? And essentially, it's now able to stabilize two rings. OK, you have to. I know that it's really funny, right? But the point is, there's probably a few papers that have tried to do it explicitly, but it's actually really hard, because if you do optimization, you know that Boolean variables cost you a lot of money when you want to solve a mixed integer linear program or any kind of program which has an integer variable. So the point is, there's almost no known article from that half century of work that has managed to, in a convincing manner, do the same thing. Here, it's exactly the same learning algorithm, except instead of training it on a single ring, you train it on a double ring. And it figured out something which you could argue maybe you learn in police academy. OK, you've now taught the software to be a policeman. But OK, the point here, and you'll see it later, I'll keep doing this. I mean, it's kind of this emergent behavior that the algorithm is able to learn. But the beauty is that you don't need to explain to it that we're going to do like what you do when you open a bridge or when you reopen something that was closed. So of course, that's the real challenge. No, we're not there yet. So for example, if you take a simple case of an 8-figure, which I'm showing here, what happens in an 8-figure is as things gets too complicated, then essentially you reverse to what you've seen probably in your neighborhood when there's a stop sign. It's like, please go. Okay, no, your turn. You go, man. You go. You go. So this is the most inefficient way, in a sense, to manage an intersection, because that's probably the solution that makes the throughput as small as it can be. But okay, if you only have a stop sign, that's what you can afford as a mayor of a city. Now here, the interesting part is that if you train the algorithm on that setting, it should start moving. Yep. Nope. Yeah. What it does is actually, you can see it waiting here. And what it's doing is it's actually picking up the right speed so that the exact length of the snake it's creating corresponds to the length of the 8-figure. Now, here I'm narrating to you what it's doing, right? I'm telling you the red car is, I'm telling you the red car is picking up the speed that manages to create a snake of the exact length. And that's because I know that underlying that simulator, there's actually something called a car following model, and the spacing between the vehicles will depend on the speed. And you know this because if you drive on the freeway at 200 miles an hour, or say maybe 100 miles an hour, you're on the German freeway, you're going to probably be relatively far from the person in the front because you're not suicidal. But if you drive at 25 miles an hour or 10 miles an hour, you can afford to be much closer. So there's a model for it. And the thing is, the red car has figured out that model without knowing that model, because that's what it used to create the snake. So another example of an emergent behavior, you never told the car following model to the red car, and you never told it the snake length either, but it figured it out. And essentially, you could argue that it kind of rediscovered platooning, because the behavior you see here is essentially platooning. In the case where you don't control, a car comes from the north or the south, and then another car comes from the east or the west, whatever it is, and then they essentially alternate at the stop sign. And here, what it said, it just essentially bundled them, and you can see the throughput is much faster. So you can see how you can progressively start teaching vehicles to do more and more. Now here's an example I cannot really narrate anymore. So now there's a combined routing dash vehicle control problem where vehicles either choose the longer route or the shorter route, and what you're trying to do is you're trying to optimize the efficiency of that intersection here. So if all the vehicles are uncontrolled, they're all humans, then the same thing will happen. Roughly, there's going to be one car go every one at its turn, which is very inefficient. And now, if you insert self-driving vehicles in that mix, then the following happens. You can see that self-driving vehicle comes here, and somehow it's holding for now. And at some point, it will figure out, I don't know exactly why, when it needs to go. Now it's going, so it's going to start releasing the queue. And then there's going to be another queue that will form, and it will hold it again and release it. But I cannot really narrate you in a convincing manner what it's doing anymore. So it figured out something that I cannot even understand, really. Obviously, if you measure the throughput at the intersection, it's more efficient, so it's doing what it's supposed to do. But it has, in a sense, superseded what even the human can interpret. And it's not rocket science. I mean, this is just car traffic here. But that shows you, in essentially, at the point at which you cross, we've crossed the first line where we're able to match what humans do with optimization and control. And now we're crossing a second line where we've essentially gone over the thing that the human can explain rationally. There's a lot of things you can do and explore with this. And one of them is transfer learning. So transfer learning has a lot of different contexts in which it can be used. The first context in which we're interested to using it is, and all of you in your field have probably done that in some form or another, you learn on a specific data set, and then you like to see how you do on a different data set. So which in the context of self-driving vehicles would translate into learning on a scenario or a set of scenarios, and then trying it on a scenario you have not seen. So the simplest way to do this is, could you train self-driving vehicles on a ring? And what would happen if you now deployed them in a new setting they have not seen, such as a merge? Okay, so let's just see that. Okay, I'll just come back to that later. So this is the merge. So you can see these vehicles are merging. And once they're merging, like now, they create this little shockwave here coming in the back. So this is a traffic jam. Let's do another one. It's having a hard time to get in. And then you can see that's piling up on the back of it. And if I just, then you can see even that's propagating backwards now. So that's, in a sense, the genesis of these stop-and-go waves. And you can argue, even on multi-lane freeway, that's what's happening, because when you have on-ramp traffic, that's what's starting to generate bottlenecks, and that's what's starting these self-perpetuating waves. So that's the baseline scenario. You can see it now, it's really propagating backwards. Okay, and these things, they happen. It's not just like a simulation. I mean, there's tons of data that show that happening for real. So the question is, can you, and you get two double now. Here's two, I don't know if you have good vision, you can see those two shock waves propagating backwards. Okay, so same setting now. We're going to inject a small proportion of self-driving vehicles, the red vehicles. And the only thing you can see is the one in front and the one behind, you know, some kind of a radar or vision-based approach here, and try to see if there's any way it could actually do something beneficial from learning through the ring. So same exact setting, but now, once in a while, you're going to see some red vehicle do something here. So you keep injecting the cars, it starts creating the problem. You can see this first one is starting to slow down a bit. Now you can see it's not doing much this time. But this one has completely stopped because it can sense the blue one here and the blue one there. And essentially what it has done is it's learned to be a traffic light. It's like you have just now taught a self-driving vehicle to become a red light or to become a flow smoother or another red light. But there's no red light, obviously. It's just learning that it should stop. But the amazing thing here is that transfer learning is actually pretty successful because it did learn to do it on, it did learn to do it on the ring, but it applied it successfully on the merge, which is really a different scenario. And the other thing to notice is that the amount of red cars it takes to make that flow much smoother is not that high. I mean, I'm not counting here, but we're probably in the 5%, yeah, 5%. And we did later some penetration studies, which I will show. So that's another thing which is quite great, is that you don't need to have 90% of the self-driving vehicle for it to become feasible or to become helpful. And so it's not also something that just works in simulation. There's interesting things to be said about automatic cruise control. This is another example that our former student Dan Work, who is now a professor at Vanderbilt, has done. So what he just went to the rental shop and essentially got himself 8 or so cars with adaptive cruise control, and then drove them on an empty street of Tennessee that he blocked for that occasion, and then started to essentially what would happen if you engaged all the adaptive cruise controllers in each of the cars, which are different brands, right? And so all of you have probably at some point in your life tried adaptive cruise control, right? It's something that if someone in front of you slows down, it will slow down. It's able to be quite responsive to your needs. But what nobody has really studied is if you put all these cars together with adaptive cruise control, is it good or bad? And in that experiment, this was a pretty scary experiment that they did. So this is the trajectory of the first vehicle, which at some point you reduce its speed, okay? Then the second vehicle reduce its speed even more. Then the next vehicle reduce its speed even more. And okay, you can see where I'm going with that. So essentially that stuff is really amplifying, but that's a bad outcome of automation, if you will. It's a sense saying that these things are nice. They make your life easier if you're the only one using them. But if we put a lot of people like you who are using it at the same time, this can become really dangerous. So he was actually in the last car. When I called him on the phone, I didn't know he was doing the experiment. And he's like, hey, I really got to call you back because it's getting really dangerous here. And in fact, it got really dangerous because at some point the ACC disengaged. And in the last car, I mean, he was oscillating between, probably 70 miles an hour to try to catch up with the previous one, and then 20 miles an hour when he was piling up, and that got really dangerous. So there's something to be said about automation, and there's something to be said about coordination here. Because the point is, this is extremely inefficient. This is supposed to make you more comfortable and more efficient when you're by yourself. But in coordination, it's really bad. And that is something that is probably happening on freeways. Like, there are freeways where a lot of people have their ACC. There's an exhausting day of work. They go back home. They're tired. And it doesn't take many of them to make this much worse. And so going back to that example I was showing with the merge, and so I'm going to just go back a few slides to show you this again. So with this setting, okay, so the point is that what the merge did is it essentially removed these waves. So these waves are the waves due to the fact that you go fast and then you go slow, and then any perturbation induces these waves. So the way it works is, remember, every time I injected a vehicle, it created that wave. So injecting a vehicle here means there's a new car appearing here, and that's the trajectory. So this is time and space. And so if this guy gets in the intersection here, then the next guy slows down, the next guy slows down, and you can see this whole thing moving backwards, okay? And then you can see all of them moving backwards. So what the automation did here, it learned from the ring to preemptively slow down in anticipation of a wave coming at it, which is essentially what it's doing here. So there's this wave happening here. It senses it immediately, and essentially the next automated vehicle that comes waits until it's released to reach it exactly at the right time. And then another car is introduced, creates that wave. Immediately, the car which is here waits and then essentially catches up when needed. So this is interesting because that's something that not only it was not trained to do, but it's also doing the right thing. It essentially is trying to fight this kind of temptation that a human would have to go as fast as possible. And so this is something that, when it came out, caught quite a lot of attention. The two students who did it is Eugene Vinitsky and Aboudi Kradier. This is their picture. They're two current PhD students at UC Berkeley. So Science did a little sequence on this. And because there's very significant implications here. And the implication is that, you know, if you had the right amount of vehicles, you could essentially smooth traffic on freeways. Now, this is just one lane, and we'll go to the kind of a real case later because obviously reality is a bit harder. But what's exciting is that essentially at 10% penetration rate, so every 10th vehicle, you could almost smooth that thing entirely. And at 5%, you could almost do the same. And so this is a very hopeful result in the sense that it's a result that is very encouraging. You know, you take some new models, take your Tesla, or take the high-end models in BMW, Daimler, other brands, and so on. The functionality required to make this happen is almost there already. If you're just doing longitudinal control, you could rewrite any kind of autopilot to do that with the proper communication. So it's not science fiction. With the proper incentives, with the proper laws, with the proper technology upgrade, that could happen literally this year. So that you can imagine with more research and also with more complex scenarios what could happen over the next couple of years. And the truth is, I mean, this happens. I mean, okay, again, it's like storm chasers. So there's people who go and Jamison chasers. But if I'm watching traffic again, very boring. But if you watch enough, you can see that this is happening for no reason, and that's probably going to back propagate. This is one. Okay, here's a wave that just propagated. Like you can see it now. It's probably going to re-back propagate. And this, if you keep watching, yeah, another one coming in. Nobody has been able to make an actual quantification of how much energy is wasted there. But based on the preliminary results we have, okay, now it's going backwards again. Based on the preliminary results we have, it's very likely that on a freeway like this, you could probably save at least 10% energy, which again is extremely high. Of course, the grand challenge would be, well, what if you could do this for scenarios which are way more complex? And so for those of you who have ever been to the San Francisco Bay Area, I'm sure you've driven through the Bay Bridge at some point, and you probably have seen this. This is the metering lights. This was installed in the 1970s. This was high-tech at the time. This made people really upset because they didn't realize why stopping at a red light would make it faster on the bridge later. Of course, now it's completely socially acceptable, and probably people even understand why. But just think backwards for a minute as to people were actually protesting this. When this was being installed. In the 80s, a faculty named Dolph May at Berkeley was the first one to do an adaptive controller for this metering light, so model-based approach for controlling the flux. And you know, it's really greatly improved the efficiency of the bridge over the decades to follow. But if you think about the way it works, it's actually pretty basic in the control, because the only thing it can do is there's this line here, and based on the traffic signal, either the car go through or don't go through, and that's the only control point you can essentially actuate if you want to manage the flow onto the bridge. So it's a pretty weak control mechanism, if you will, in the control theoretic sense of the term, in that once people are passed, you can't control them. And so here, what the approaches like the one I've shown before would enable is this type of approach. So on the right, you have what would happen if you just let people go. And at some point, inevitably, they clog. That's called a bottleneck, and that creates something called a capacity drop. That's a phenomenon which has been known for decades in traffic engineering. But if you selectively hold the vehicles, according to this, which again I cannot describe because this is something learned from deep reinforcement learning, so there's no interpretable thing here, is that somehow it figured out how to distribute the holding cars, then it never clogs, and it's actually way more efficient. Now, of course, this is going to probably create road rage or people shooting at empty cars that are holding them. I mean, socially, no, I mean, so this is the beginning of maybe the war of the roads where people start shooting at each other's cars. But it's not, I mean, think about it 80 years ago when the first person showed up at an intersection, saw a traffic light. Of course, the intersection was empty. It's red, so they have to stop, and they're probably pretty pissed that they have to stop because there's no reason to stop. There's nobody there. And of course now, well, there are countries in which you don't respect the traffic laws and the traffic lights, and I might come from one originally. But in general, people have accepted the existence of red lights and usually stop at red lights. So it is going to take some time before people accept that suddenly there is a really annoying vehicle that potentially is actually empty because it's a robocar that is in front of you and not moving for the greater good. And that might be even harder to accept if there's actually someone in this car who has volunteered his car to be a flow pacifier. But that will happen at some point, and that's one thing we're really excited to work on because I think this is the future of traffic control. So, of course, this is all in software. And before you start to wreck hardware, you try it in model work. So we started working with my good friend Andreas Malikopoulos from the University of Delaware on what we used to call the mini city or the scaled city. And so the scaled city is a model of the city that he built to essentially start to see how to migrate software algorithms into hardware, which all of you who have done any hardware work in robotics know is really hard. Very important feature, it has a French cafe, which actually serves croissant if you look on the terrace. And this is my daughter Miriam, because of course the kids love that because they can go to the basement and they can drive the cars remotely from the basement through a visual interface. It's actually really awesome. And that's something that Andreas routinely uses to essentially study human-machine interface. The point here is not to show the test bed. The point, which is amazing, and if you're in Delaware, it's worth stopping by. It's really awesome. But the point is to show that the next stage of this work was to be able to demonstrate the policy transfer, where now you're really transferring the policy to hardware. And that's work that Kathy Jank, who is here in the front row, and Eugene Vinitsky, who is currently interning at Tesla, did work on. And so what I'm going to show here, I'm going to try to narrate it, even though that's not exactly what happened in the reward function, but try to give you a narratable depiction of that movie. On the left, you'll see a baseline scenario in which there's a given demand profile on the roundabout. So there's cars coming here, cars coming out, coming here. They're all going this way, and you try to, it's not exactly what we did in the reward function, but you try to essentially push the car as fast as possible outside of the roundabout. So if you're just humans, then essentially it's going to be a selfish thing. People come in, try to enter this as fast as possible. Whoever comes first gets the first pass, and then that creates some form of inefficiency. And then on the right is going to be the same scenarios, but the blue cars are playing the role of these flow pacifiers. And what I'm asking you to watch when I play the movie is the exit time of the last vehicle that exits the roundabout. And you'll see that in the case of the reinforcement learning, that time happens earlier. So you can see these vehicles entering here. And somehow what happens is these vehicles are being held here. And the Hummer, which is going to be the last one exiting here, essentially happens to be the last one when here is overtaken the two at the roundabout, resulting in the fact that these guys exit later. So okay, this is still a simple scenario, but the point of this scenario is to show that you can do transfer learning efficiently into hardware, even though I mean, obviously the goal being to learn in software and develop in hardware and run in hardware. Now, I want to finish the talk by talking a little bit more about future things we're interested in, and in particular N2L pixel learning, because it ties in very nicely with some of the work done in the video game industry. And this work was done by Feng Yu Wu, who is sitting in the back of the room here. So from a classical modeler's perspective, trained in the physical sciences, and from a classical optimization and controls person, I've already committed a very big and bad crime, which is essentially I got rid of the model in the genesis of the algorithms I've shown before. And that usually would freak out anybody classically trained in control, such as myself, or in optimization, because I think part of the benefits of using a model-based approach that at least people resonate with both in industry and in academia is that you can prove something about it. And a lot of the work in optimization, in control, and even in some subfields of machine learning have to do with proving that if you believe that model is good within this bound, so find your robustness margin in whatever norm you prefer, then you can prove that the system behaves that way. And that, in a sense, you can argue has been discarded as soon as I started to not use the model and train the policies by software. Now I'm going to commit another crime. I'm going to actually remove the state space. So state space is what's commonly referred to in control theory or optimization as the state of your system. So position, acceleration, lane, altitude, whatever parameters. So traditionally refers to as XT in control theory or ST in machine learning, different notations for the same thing. And even though in the previous case it's model-free, right? Model-free meaning it's essentially not using a model other than learning in the simulator, I'm still using the state space of the simulator to produce my policy, which I need. Essentially, I'm using the fact that the simulator is able to spit out the position, velocity, and all the parameters in order to create my policy. What if I just try to remove it? So in other words, what if instead of learning from the state space, I was learning from a representation, like a picture of the state space. So typical reinforcement learning loop, the agent has some action. You plug it into the simulator, that's the environment. The simulator will spit out the state space and a reward. And then you feed in the reward, and based on the reward, you do better, and that's how you improve your score. So the traditional thing in reinforcement learning. But that assumes that, okay, that classical paradigm of reinforcement learning makes it such that you learn from the state space. But what if we decided to not have it? So in other words, instead of learning on the state space, what if you learn on a picture of the state space? And there's many reasons why you would want to do that. I mean, for once is that state space grows exponentially, or complexity of using the state space grows exponentially with the number of vehicles. It's complex. But instead, if you learn on the picture has the same complexities, same number of pixel by number of pixel. So that's one reason why you want to do it. And okay, you want to do it maybe on a few pictures in a row because you want to learn a little bit about the system. And so that's the second crime, I guess, that I'm committing today. And after that, no more crime, I'm legal. But this is a bit disruptive because first, it's never been done before. But the reason why it's disruptive in a positive manner is that there's a lot of places in the world where you have a picture of traffic, but you don't have access to the state space of traffic, which is a good justification of why you might be interested in doing that. And so without going into the detail of how you would train your reward function for that, the one thing which is interesting is that essentially if I go back to that picture of Minicity, learning from the representation, so if you want to do end-to-end pixel learning, it amounts to learning from a movie of traffic. And probably now a lot of you are thinking Atari game and a lot of the different video games that have had great successes in learning from. And that's exactly what you want to do here. And one of the reasons why you would want to do this is that in many cases, it might be easier to get access to that representation of traffic in addition to potentially streamlining the complexity of the process of doing it. So learning from the pixels or learning from the rendering of traffic amounts to learning from this. And this is maybe not completely realistic because if you ever wanted to learn this, in a sense, it might mean that you want to hover a helicopter over the city, keep filming and learning from that. So the real objective maybe is not so much to learn from a centralized view of the city, if you will, but maybe from a decentralized view where it's fair to assume that what you should know about is not so much the city itself, but what the vehicle sees. So these little circles here, or disks, are essentially whatever a vehicle at the center of the circle can see. So it's the same, it's an excerpt of that movie, but you can see the circles moving. because that's fair. I mean, you think about any car today has a lot of cameras, has abilities to sense around itself, has the ability to also communicate with the infrastructure, and is connected. And so part of the work that Fengyu has been doing over the last 6 to 12 months is understanding how the performance of the learning algorithm, such as the one I've shown before, translates if now you commit that second crime, which is essentially removing the state space and learning from the pixels. And the good news is that this works quite well. And in fact, so I'm showing the performance in the previous slide here. But the preliminary results we have is that both on the circle case that I showed before and on the 8-figure that I showed before, the results are already comparable. And so that's the second disruption. I mean, I think it was pretty shocking already to a lot of people that you could do a better job at the ring without a model than if you had a model. That's shocking. But now what's even more shocking is that you don't even need the state space of the ring, you just need a picture of the ring. And that's probably just the beginning of a set of disruptions that are going to come, because if you think about segmentation, so now putting the three together, probably a lot of the talks you've seen when you were at that conference are talks like this, where people show you their latest deep learning algorithm to identify features in traffic. So there's a bunch of human labelers that at some point spend a lot of time sitting, labeling cars, or you did actually with all these authentication algorithms that you see. So, I mean, I don't want to say that problem is solved, but I think that problem will probably, or the solution to that problem will probably be a commodity in a few years. Like, I think we're not that far from having, you know, there's already a bunch of dashcam companies that will provide you a dashcam that can do things here and there. So the notion that, you know, this is something that you can buy for a few $100 that is connected and doesn't even need to send all the rendering, just sends whatever information is gathered, that's almost, that's going to happen very fast. And also the notion that from that you can identify the relative speeds of the vehicles, the relative positions of the vehicles by some pose estimation and some relative velocity estimation when you interface this with any kind of inertials that are on board the vehicles, that's also not that far. So all I'm saying here is that this, which is conceptually obtained from rendering software, that data that we can learn from this here, in a few years, we will be able to learn it because that will become a commodity. Because every car manufacturer will have that streaming already in their system. Some will be willing to share it. So it's only a few years before this and this becomes the same. And that's very exciting because now, progressively, we're removing all the barriers that have prevented us for half a century to do these multi-coordination algorithms and to learn from these gigantic sets of data that were either untractable or we weren't able to obtain. And so this is where, let me just try to see, okay. This is where it ties in with the video game example I showed before. You probably all have seen on YouTube these videos of the Google DeepMinds at Q-Learning. So essentially, I mean, I was born in 1974, I grew up in the 70s. I used to play these Pong and games like this. And I mean, for those of you who have played these games, and you know that if you're a young child, it's not obvious. I mean, it will take a few hours before you become good at it. And what's amazing with the pixel learning techniques that were deployed here is that not only did the algorithms learn how to play that game, but it even learned what took years or at least months to practice, which is, you probably remember if you're playing this, that the most efficient strategy is you dig a tunnel, because then you can stuck the ball on the other side, and then it does all the work for you without you having any jeopardy of missing it. So as a child, it was taking a lot of time to learn that. And what's amazing is that if you keep watching that video, at some point it will learn to do it, and it will become really, really good at it. And the interesting part is that that algorithm is essentially the same as the one we're using to learn traffic. And so video games were one of the first battles that was won. So that's this clown. The ball already exploded. You see, it's digging the hole now. Not yet. Maybe that's the next iteration. It'll finally do it. So that's that. OK, here we go. OK? So it learned to do it. Something that we could rationalize as kids, it learned how to do it. The obvious other example is AlphaGo, which was the big breakthrough. And so really, I mean, this balloon will take a lot more to explode because it's much harder. But that's the same spirit, is that what if you could learn and do it from the perspective of learning it from the rendering rather than the access to the state space. And so that's the whole paradigm shift that, if you will, we see in the field of mixed autonomy and self-driving vehicles, but automotive in general, is that for the types of work we do, it is most likely going to be the approaches that kills it. Now, it could not have happened some time ago, and also it's not good for everything. I mean, so using deep reinforcement learning for multiple vehicle coordination like we do, no problem. I'm a believer. Using deep reinforcement learning for safety critical things, that gets me a lot more nervous, because I don't want a corner case while I'm 30,000 feet on an aircraft or 150 miles an hour on the car, and suddenly it's facing a problem it's never seen before. So I think the key is also to use that paradigm of deep reinforcement learning in a context where it can make a difference, and it clearly does, but in a context where it's also not dangerous to do it. And that's the computational framework that we've built with the generous support of Amazon. We were one of the early grants of the academic program that was created by AWS when they were trying to get us to use the tools. And that was really great, because what it enabled us to do is what was the first integration of 3 components, without which everything I've shown before would not have been possible. The first component is these traffic microsimulations. The second component is the deep reinforcement learning libraries, which have extremely rapidly evolved over the last couple of years. And the third component is the cloud. And these are the 3 edges, the 3 vertices, sorry, of this triangle. Microsimulations have been there for 2 decades. And none of it is possible because none of it scales. And in particular, all the data and all the things I've shown before. Deep reinforcement learning, that's the ingredient that makes it work, and that is disruptive and even shocking to some people. And the cloud is the only way to make it scale and to make it ubiquitous and to, in a sense, enable a lot of different platforms to run together. So looking forward, so we started with Sumo because it was an open source thing, and so you can download it from our website. It's all reproducible. Later, Siemens became really interested, so now we have a second microsimulator here. And I think the takeaway message is that you can put any simulator you want. You could probably even learn on the collection of simulators, because essentially it's just giving you a richer environment in your, if you remember, in the deep reinforcement learning loop. So this is going to be richer and richer. The more simulators you can put on the cloud to learn over, the more the policies you learn will be rich and able to do things which are more challenging. So if you're, and so where are we going with this also is like, we're not there yet, obviously. I mean, today I showed you a single ring, I showed you a double ring, I showed you an 8-figure, some on-ramp, off-ramps, there's more geographies we do, but certainly, okay, we've got a lot of Lego blocks, but we need to build an Eiffel Tower. And we've maybe built a little mini Eiffel Tower. Like we still have a lot to go. And oops, sorry. And so that means learning on more complex scenarios and also generate richer policies. So we also are excited because there's a user community. We've been growing for now quite some time. If you're interested, you can go to our website, flowproject.github. And so you can download the framework. You can run it on the AWS cloud. There's benchmarks that we released. There's starter problems. So it's hopefully we'll be able to grow a community and in turn be able to develop new tools that can migrate to hardware. I think the exciting thing this year for us is that there's a lot of automotive companies that have started to really pay attention to this because, again, it's not science fiction. There's at least 10 models today that can support some of the algorithms we've done. That doesn't mean it rolls tomorrow because there's issues of certification. You can't just do whatever you want with it. But it's not long-term science fiction. It's really something which is around the corner. And maybe this is the second to last slide I want to show. I mean, many of you have used Mujoko and have, you know, if you're a roboticist, the process of benchmarking is something you're familiar with because you want to essentially benchmark your algorithm versus other algorithms. So last year at Coral, we released the first traffic benchmarks, which you'll recognize from the earlier part of the talk. And that's exactly the point, is that, you know, the debate between model-based and not model-based, or physical domain-based and simulation-based, I mean, that debate will never stop. And that's a philosophical debate. It's a healthy debate because the truth is the optimal point is probably in the middle. It's neither on one end or the other. But That's exactly why we want benchmarks. So in the same way that Mujoko enabled a whole slew of interesting scientific production because it enabled people to benchmark on specific cases of robotics, what we hope to achieve, and hopefully with a lot of you contributing, is growing the set of benchmarks that can be used to essentially enable all algorithms to compete, and not only deep reinforcement learning based algorithms, but all algorithms, model-based or other approaches. Finally, again, want to really re-express my warmest thanks to Amazon for their support, for inviting me to this conference, and also tell you we're trying to grow our community. So obviously we're a small group. There's 10 PhD students. We can't do workshops all the time, but we are trying to do more and more tutorials because we're receiving a lot of interest from automotive, the private sector, other universities, and even government organizations. So the next one we're doing is on the French Riviera, if you are interested in going to an exotic place for, legally for your work, to work, right? So we're going to do our next tutorial there in Nice, in France, a little bit later this year. So I think I'm out of time, or nearly out of time, and I think now is the time for everybody to go and gamble all their money. Thank you.